Somewhere in the vast darkness of space, a star has just been torn to pieces. Not by an explosion, not by a collision, but by the invisible, irresistible pull of gravity itself. A black hole, wandering alone through the cosmos. It's passed close enough to a distant star that the fundamental forces holding the star together have been overcome. The star is being shredded. Its material is being stretched and heated to millions of degrees. Its death throes are radiating energy across the electromagnetic spectrum. And for the first time, humanity has been able to witness this cosmic catastrophe in real time. This is the story of one of the most terrifying and beautiful events that can occur in the universe. This is the story of a star's final moments. And what we've learned from witnessing this death is forcing us to reconsider how common such violence truly is in the cosmos. For most of human history, we didn't even know black holes existed. They were theoretical constructs, mathematical solutions to Einstein's equations of general relativity that seemed too extreme, too impossible to exist in nature. A black hole was a point in space-time where gravity had become so extreme that it bent reality itself, a region where the curvature of space-time became infinite, a place where the very laws of physics as we understood them broke down. No light could escape from inside a black hole's event horizon, the point of no return. Anything that crossed that boundary was lost, forever swallowed into a void from which no information could return. For decades, scientists debated whether such objects could actually form. Could massive stars really collapse so completely that they became black holes? Or was it just a mathematical curiosity, something that emerged from Einstein's equations but never manifested in the real universe? Then came the observations. In the 1960s, astronomers discovered objects that emitted intense bursts of radio radiation, called them quasars, quasi-stellar objects, because they looked like stars, but exhibited behavior unlike anything else in the sky. These quasars were extraordinarily bright, some of the most luminous objects in the entire observable universe, yet they were incredibly compact, suggesting that their energy was being generated in a region smaller than our solar system. The only way to explain that much energy coming from such a small space was if a black hole was at the center, pulling material from surrounding stars and heating it to billions of degrees as it spiraled inward. Black holes weren't just around these supermassive black holes was so extreme that it warped space-time into shapes that defied intuition. Matter orbiting at millions of kilometers per hour, space-time twisted into geometries that would drive human comprehension to its limits. These black holes were the engines of galaxies. Their gravity determined how galaxies formed, how they collided, how they evolved. Understanding black holes meant understanding the universe itself. But there was a mystery. Black holes were supposed to be stationary, anchored at the centers of galaxies by their tremendous mass. Yet there was evidence that some black holes were wandering, that they'd been ejected from their homes. They were drifting alone through the cosmos, orphaned, cut off from the active feeding that fueled the most luminous phenomena in the universe. How could a black hole be ejected? The answer lay in the dynamics of multiple black hole systems. When two galaxies merged, their central black holes didn't immediately combine. They orbited each other for millions of years, locked in a deadly dance. If a third black hole entered the system, three black holes were interacting in the same region of space, chaos could ensue. In some cases, one black hole could be ejected at tremendous velocity, rocketing away from the system like a cosmic bullet. Speeds of thousands of kilometers per second, fast enough to leave the galaxy, fast enough to wander through intergalactic space alone. For decades, astronomers had predicted that wandering black holes existed, that they drifted silently through the void between galaxies, that occasionally one of these wanderers might pass close to a star, and if the encounter was intimate enough, it could tear the star apart. A tidal disruption event, scientists called it. The black hole's gravity would be so extreme on one side of the star, compared to the other, that the difference in gravitational pull would exceed the force holding the star's material together. The star would be stretched, elongated, torn into a stream of matter spiraling toward the black hole. The friction between the matter would generate heat. The collision of particles would produce radiation across the entire electromagnetic spectrum. For a brief period, this dying star would shine brighter than billions of ordinary stars combined. But observing a tidal disruption event was extraordinarily difficult. These events were rare. They lasted only weeks or months before the star was consumed entirely. And they happened in distant galaxies, billions of light years away. A telescope would have to be pointed at exactly the right place, at exactly the right time, to catch one in progress. The probability of such a detection seemed vanishingly small. And yet modern survey telescopes changed the equation. These telescopes scanned the entire sky repeatedly, looking for objects that appeared suddenly, brightened rapidly, then faded away. Transient events, supernova, gamma, ray bursts, tidal disruptions. By searching systematically, astronomers could find these rare catastrophes. In 2019, a tidal disruption event occurred in a galaxy about 400 million light-years from Earth. A wandering black hole, invisible and alone, had passed too close to an ordinary star orbiting that distant galaxy. The star never saw it coming. Black holes don't announce themselves. They don't emit light or radiation when they're just passing through empty space. They're invisible. They're silent. They're the perfect predators, moving through the cosmos without warning. But when the black hole got close enough, the star's fate was sealed. The gravitational gradient, the difference in the black hole's pull across the star's width, exceeded the star's self-gravity. The star began to break apart. It happened gradually, then suddenly. First, the outer layers of the star began to separate. Material from the far side of the star experienced less gravitational pull than material on the near side. The star was being stretched like taffy. The pressure and density in the star's core rose as the outer layers separated, increased. The star's surface began to break apart, streams of gas flowing away from the main body, drawn toward the black hole. As the star's material got closer to the black hole, it accelerated. The velocity increased. Material that had been stationary, orbiting its own star's core peacefully, was now being flung at velocities approaching the speed of light. Temperatures soared. Atoms collided violently. The star ceased to exist. In its place was a stream of superheated plasma, a river of matter flowing toward an invisible abyss. Telescopes pointed at that distant galaxy detected the catastrophe. The radiation signature was unmistakable. X-rays, ultraviolet light, visible light, infrared radiation, all being produced as the stellar material was heated to incandescent temperatures by friction and gravitational compression. The tidal disruption event was the brightest object in its galaxy. For a few weeks, this dying star outshone billions of ordinary stars combined. Then gradually the brightness faded. Supply of material flowing toward the black hole diminished as more of the star was consumed. The accretion disk, the whirling maelstrom of stellar materials circling the black hole at nearly light speed, continued to emit radiation. But the intensity diminished. Over months, the brightness dropped. Over years, the event faded into obscurity, becoming just another chapter in cosmic history. But the detection of that tidal disruption event raised profound questions. How often did such events occur? Were wandering black holes common? Was this a rare catastrophe or a routine cosmic event? If wandering black holes were plentiful, if they drifted silently through billions of galaxies, then perhaps many stars met their ends this way. It's not through supernova, which occurred when a star exhausted its nuclear fuel. Not through mergers with other stars, but through the chance encounter with a gravitational predator. A black hole that had been ejected from its home and was now hunting through the dark void. To answer these questions, astronomers needed more data. They needed to survey the sky systematically, identify tidal disruption events as they occurred, and build statistics about their frequency. Several survey missions were designed for this purpose. The Zwicky Transient Facility in California, the Pan-STARRS Survey in Hawaii, the Atlas Survey. These telescopes scanned the sky repeatedly, looking for objects that change brightness between observations. Each night they would photograph thousands of galaxies. Each new night, they would photograph them again and look for differences. A galaxy that was bright last. Night but dim tonight. A galaxy that was dim last night but bright tonight. Those changes indicated something had happened. Something had changed in the darkness beyond. What emerged from these surveys was a new census of cosmic violence. Tidal disruption events occurred roughly once every 1,000 to 1,000,000 years per galaxy. That sounded rare. But multiply that by the hundreds of billions of galaxies in the observable universe, and the numbers became staggering. Thousands of stars were being torn apart every year. Every single day, somewhere in the cosmos, a star was encountering a wandering black hole and being destroyed. The universe viewed through this lens was far more violent than anyone had appreciated. It wasn't just a peaceful realm of stars burning steadily for billions of years. It was a battlefield, a realm of dangers that most stars would never encounter. But that ensured that cosmic catastrophe was continuous and relentless. Understanding tidal disruptions required understanding the physics of extreme gravity. Black holes' gravity follows the inverse square law just like any mass. But what makes black holes unique is how much mass is concentrated in how small a space. The intuition. An astronaut falling toward a black hole would experience what's called spaghettification. The gravity on their feet would be so much stronger than the gravity on their head that the difference in force would exceed the strength of the human body. They would literally be stretched into long, thin strands. A star, vastly larger, but similarly unable to withstand the gravitational stresses, experienced the same fate. It was torn apart, not by impacts or collisions, but by the simple geometry of gravity and curved space-time. But the matter torn from the star didn't simply fall into the black hole. It formed an accretion disk, a whirling maelstrom of material orbiting the black hole at nearly light speed. The material in this disk was heated to millions of degrees. Particles were moving so fast that collisions between them produced enormous temperatures. Electrons were torn from atoms. Plasma was created. Radiation was generated across the entire electromagnetic spectrum. Friction between particles in the disk converted kinetic energy into heat, which was radiated away as light. That light is what astronomers detected when they observed tidal disruption events. They were seeing the last moments of a star, watching its energy being converted into radiation as it was consumed by a black hole. But there was something profound about these events that went beyond the physics. These were deaths on a cosmic scale. A star that had perhaps existed for billions of years, that had steadily burned its nuclear fuel, that might have hosted planets orbiting around it, that might have been orbited by worlds where life had emerged, was being destroyed in an instant. In the timeline of the universe, the death was swift. Over days or weeks, a star that had existed for eons was gone. Its material was consumed. Its planets, if it had them, were flung into space or torn apart themselves. Any life that might have existed on those worlds was extinguished. All of that history, all of that potential, was erased. The implications for the fate of Earth were sobering. Our sun orbits at a distance from the galactic center where wandering black holes are rare. But in a few billion years, the Milky Way galaxy will collide with the Andromeda galaxy. The merger will be catastrophic from a planetary perspective, though gradual enough that Earth would almost certainly survive through the collision as a gravitationally bound system. But during the merger, the dynamics of black holes at the center of both galaxies would interact. Black holes could be ejected. The overall distribution of black holes in the resulting merged galaxy could change dramatically. It's possible, though unlikely, that a wandering black hole could pass through the solar system millions or billions of years from now. If one did, and if the encounter was close enough, it could tear the sun apart. Humanity's home star could be destroyed by an invisible predator. The thought was both terrifying and humbling. It reminded us that no place in the universe is truly safe. No home is truly permanent. Even the sun, which seems so immutable, so eternal in human timescales, is vulnerable to cosmic forces beyond human comprehension. Yet there was something magnificent about the tidal disruption events that telescopes were detecting. They were moments of extraordinary revelation. They revealed the presence of black holes that otherwise would have remained invisible. They demonstrated the incredible power of gravity. They showed how matter and energy interacted in the most extreme environments. They were laboratories of physics that couldn't exist anywhere else in the universe. A black hole tidal disruption was a glimpse of reality at its most extreme. a window into physics that human laboratories could never replicate. In a sense, these dying stars were giving us a gift. They were showing us how the universe really worked. They were teaching us lessons about gravity, about space-time, about the nature of reality itself. The detection of wandering black holes also raised a profound mystery. If black holes could be ejected from their parent galaxies at high velocities, where were they going? Were they escaping to intergalactic space, doomed to wander eternally in the darkness between galaxies? Were they being recaptured by other galaxies? Were they colliding with each other? The physics of black hole dynamics in intergalactic space was poorly understood. These orphaned black holes were like cosmic ghosts, invisible unless they encountered a star. Most would wander eternally, never encountering anything, never betraying their presence to distant observers. But a few would cross paths with stars. A few would create the spectacular tidal disruption events that astronomers were beginning to detect with modern telescopes. As observations accumulated, a clearer picture began to emerge. Tidal disruption events were more common than anyone had predicted. Telescopes discovered dozens per year. The galaxy population was full of them. Some of the tidal disruptions seemed to involve black holes at the centers of galaxies, capturing their own stars. Other events appeared to involve wandering black holes. The physics was complex. The timescales were vast. But the pattern was clear. Stars and black holes were interacting. Matter was being converted into radiation. The universe was far more dynamic, far more violent, far more filled with dramatic events than a casual observer would ever realize. What made this even more profound was that these tidal disruption events allowed astronomers to study black holes in completely new ways. When a black hole was actively feeding, accreting matter at high rates, it produced radiation across the entire electromagnetic spectrum. Telescopes could observe this radiation. They could measure the brightness, the color, the variability. From these measurements, they could infer properties of the black hole, its mass, its spin, the structure of the spacetime around it. A tidal disruption event was a temporary window into black hole properties that would be hard to study any other way. Each event was a unique opportunity to learn something new about how black holes worked. The implications extended even further. If wandering black holes were common, if they drifted through space from galaxy to galaxy, then perhaps they carried a message encoded in the gravitational waves they produced. When a black hole tore a star apart, the matter flowing into the black hole didn't sink silently. It produced ripples in space-time itself. Gravitational waves. In principle, sufficiently sensitive detectors could measure these waves, could hear the death cry of a star torn apart by a black hole. In 2015, the LIGO Gravitational Wave Observatory detected gravitational waves from two merging black holes. It was humanity's first direct detection of gravitational waves. Since then, LIGO and its sister observatory Virgo had detected hundreds of events. Merging black holes, merging neutron stars, binary systems spiraling together, and with each detection, the universe revealed itself more fully. Tidal disruption events, it turned out, were also sources of gravitational waves. In principle, when a black hole shredded a star, the gravitational waves produced should be detectable by current instruments. They would carry information about the black hole's mass, the star's mass, the geometry, the encounter. They would provide data that no other observation could provide. Astronomers were beginning to combine electromagnetic observations of tidal disruptions with searches for associated gravitational wave signals. When a tidal disruption event was detected in a galaxy, gravitational wave detectors would search for signals from that location at that time. Sometimes they found nothing. But sometimes a gravitational wave signal would be detected, corresponding perfectly to the electromagnetic observations.
Ow!
When that happened, it was a triumph of multi-messenger astronomy. Using multiple forms of radiation and gravity waves, astronomers could paint a complete picture of a cosmic event. They could understand what had happened, how it had happened, and what it revealed about the universe. These discoveries were transforming our understanding of the cosmos. For centuries, humans had viewed the universe as relatively static. Stars were eternal. Galaxies were stable. The universe changed on timescales so vast that change seemed impossible within human lifetimes. But modern astronomy had revealed the universe as fundamentally dynamic. Stars were being born in vast molecular clouds. Stars were dying in supernova and collapsing into neutron stars and black holes. Galaxies were merging. Black holes were wandering. Matter and energy were constantly being rearranged, recycled, transformed. The universe was alive with activity, violence, and creation were intertwined. Death led to new birth. Stars consumed by black holes had their matter eventually released through the black hole's accretion disk, influencing the evolution of entire galaxies. The tidal disruption events were just one example of this cosmic dynamism, but they were a vivid, dramatic example, he showed. The universe not as a museum of eternal objects, but as a realm of change and transformation. They showed how gravity, the force that seemed so gentle in human experience, could become a tool of destruction on cosmic scales. They showed how matter and energy interacted in the most extreme environments, and they revealed that the cosmos was vastly more interesting, vastly more complex, and vastly more dangerous than humans had ever appreciated. As telescope technology improved, as gravitational wave detectors became more sensitive, as computer algorithms became better at identifying rare transient events, the rate of tidal disruption detection increased. What had seemed like exceptional events became routine. Every night, somewhere in the cosmos, a star was being torn apart. Every day, humanity could point its telescopes at distant galaxies and find evidence of stellar destruction. The knowledge of this ubiquitous violence might have seemed depressing, but many astronomers found it inspiring. It was proof that the universe was far richer, far more complex than anyone had imagined. It was evidence that fundamental physics was constantly playing out on cosmic stages. It was a reminder that there was still so much to learn, so many mysteries to solve, so many wonders to discover. The future promised even more revelations. Next-generation gravitational wave detectors would become operational in the coming years: the Einstein telescope, the Cosmic Explorer. These instruments would be thousands of times more sensitive than current detectors. They would detect gravitational waves from distant tidal disruptions that weren't bright enough to observe electromagnetically. It would hear the screams of stars being torn apart across the entire observable universe. They would allow astronomers to build a complete census of black holes, including the population of wandering black holes. They would reveal how black holes influenced galaxy evolution. It would answer questions that currently seemed unanswerable. And as this knowledge accumulated, the picture of the universe would continue to transform. We would realize that the cosmos is not a peaceful realm of steady burning stars, but a dynamic environment where catastrophe is constant, where violence shapes the structure of galaxies, where creation and destruction are two sides of the same cosmic coin. We would understand that our own sun, our own galaxy, is not immune to these forces. That millions of years in the future, the Milky Way will merge with Andromeda. That in billions of years, the dynamics of that merger could eject black holes into unexpected encounters with ordinary stars. That Earth itself, secure in its orbit around the sun, could eventually face a fate as dramatic as the tidal disruptions we observe in distant galaxies. But there was something else, something that went beyond the physics and the mathematics. There was the profound realization that humanity, through science and technology, had developed the ability to witness these distant catastrophes could look at a galaxy billions of light years away and detect the moment a star was torn apart. That we could measure the properties of black holes from gravitational waves propagating across the universe. That we could understand, with reasonable certainty, what was happening in these extreme environments. That knowledge was power. It was also wonder. Every tidal disruption event detected was a confirmation that human understanding of the universe was advancing. That the mysteries that had seemed inscrutable were slowly yielding to observation and analysis. The wandering black holes that drifted through the cosmos were invisible servants of knowledge. They were lonely travelers in the darkness. But occasionally, when they passed too close to a star, when they encountered another object by chance in the vast void, their presence became known. Their gravity betrayed them. The death throes of their victims revealed their existence. And in witnessing those deaths, humanity learned something new about how the universe worked. Something new about ourselves. Something new about our place in a cosmos far stranger. It's far more violent and far more beautiful than we had ever imagined. The stars that were torn apart by these wandering black holes were not lost. They were transformed. Their matter and energy were redistributed into the universe. Their deaths contributed to the ongoing story of cosmic evolution. And their deaths were observed, recorded, understood, in a sense. Through the eyes of humanity's telescopes and detectors, these dying stars achieved a kind of immortality. They became teachers. They became revelations. They became windows into the deepest mysteries of existence itself.